The word statistics is constantly being misused. During broadcast of NBA basketball, NFL football, or Major League Baseball games, sports announcers report statistics as they call televised games. Most of the time, these statistics are parameters, but the word parameters has less cachet than does statistics. Baseball statistics sounds more impressive or scientific than baseball parameters. Derek Jeter's lifetime batting average at the start of the 2010 season is .317. This average is technically a parameter, not a statistic, and is a proportion, not an average. This average is compiled by dividing his 2,747 hits by his 8,659 at-bats. Hence, Jeter's lifetime batting average of .317 means 31.7% of his at-bats result in a hit. Now, if I count his hits and at-bats in 30 randomly chosen games he played in over his 15-year career with the New York Yankees, the ratio of these two would be a statistic called the sample proportion, and it'd be really, really, really close to his lifetime batting average of .317. Parameters are computed using data from the entire population. In most cases, computing parameters is not possible, feasible, or cost-effective. Imagine how much it would cost to ask every voter in America every day if they were going to vote for then presidential candidate Barack Obama. There are roughly 120 million voters in America. Asking 120 million voters every day this same question is infeasible. It requires millions of people to conduct daily surveys. The cost of such a survey would be in the millions of billions. Instead, polling companies like Gallup and Rasmussen sample roughly 1,000 likely voters. Statistics are computations using data collected after sampling a population. If the sample is representative and random, a statistic like the sample mean or sample proportion will be close to the population mean or the population proportion, both of which are parameters. The difference in a parameter and a statistic should get smaller and smaller and smaller as the size of the sample gets bigger and bigger and bigger. Data are facts and figures collected, analyzed, and summarized for presentation and interpretation. Elements are the entities on which data are collected. For example, Data RAM, Energy South, Keystone, Landcare, Psychomedics are the names of the elements in this data set. Elements could be states, names, patients' names, welfare recipients, case identification numbers, student identification numbers, etc. There are three variables in this particular data set, which includes the stock exchange in which the company's stock is being bought and sold, annual sales in millions of dollars, and earnings per share in dollars. The column of data below a variable represents a set of observations of that variable. The first column is not a variable. The row of data to the right of each element name is an observation. For example, the second row of information highlighted in yellow is the second observation of the data. Since it is in the second row of the data set, it can also be referred to as the Energy South observation. The data set is the information, stock exchange, company stock is traded on, annual company sales millions of dollars, and earnings per share of company stock, that is collected on the companies being studied, the element names. A variable has nominal scale if the data for this variable consists of labels or names used to identify an attribute of the element. Non-numeric labels or numeric codes can be used. For example, students at a university are classified as business, humanities, education, economics, mathematics majors, etc. These labels are non-numeric. Note the names or banner ID numbers of students in such a data set are the elements. A numeric code could be used instead. For example, the variable major could equal 1 if the student is a business major, or equal to 2 if the student is a humanities major, or equal to 3 if the student is an education major, and so on. A variable has ordinal scale if the data exhibits the properties of nominal data and the order or rank of the data is meaningful. Non-numeric labels or numeric codes can be used. For example, students at universities can be classified by their class standing using non-numeric labels such as freshman, sophomore, junior, or senior. Or customers could be asked if the cleanliness of the restaurant was excellent, good, or poor. A numeric code could be used instead of the label. For example, the variable class standing could equal 1 if the student is a freshman, or equal 2 if the student is a sophomore, or equal 3 if the student is a junior, and equal to 4 if the student is a senior. Restaurant cleanliness could be set equal to 1 if a restaurant has poor cleanliness, 2 if good cleanliness, or 3 if excellent cleanliness. A variable has interval scale if the data exhibits the properties of ordinal data, and the interval between observations is expressed in terms of a fixed unit of measure. Interval data are always numeric. SAT scores are a good example of a variable with interval scale. Since the minimum score on the SAT is 600 or 10 on each section, no one taking the SAT can receive a score of 0. Generally speaking, if 0 is not a theoretical possible outcome of a numeric variable, the variable has interval scale. If Melissa's SAT is 2,000 and Kevin's is 1,000, we cannot say that Melissa did twice as good as Kevin, but we can say she scored 1,000 points more than Kevin did. A variable has ratio scale if the data exhibits the properties of interval data and the ratio of any two values of the variable is meaningful. Hence, like interval data, racial data are always numeric. Examples include variables such as distance, height, weight, time, income, and number of kids per family. If 0 is theoretically possible, the variable has ratio scale. When 0 is present in a variable, the ratio of any two values of a variable has meaning. Melissa's SAT score of 2,000 is not twice as good as Kevin's score of 1,000, because the lowest score is 600. If Melissa has earned 36 credit hours and Kevin has 72, Kevin has twice as many credits as Melissa, because 72 divided by 36 equals 2. The ratio 72 divided by 36 has meaning because students could have 0 college credits. Data are either categorical or quantitative. Labels or names are used to identify an attribute of each element. Categorical data are often referred to as qualitative data because the data can be grouped in categories because each element has an attribute or quality. Hence, categorical data has either nominal or ordinal scale and can either be numeric or numeric. Statistical analyses are limited to frequency tables, bar charts, and pie charts. Quantitative data uses numeric values to indicate how much or how many. Quantitative data is discrete if measuring how many. For example, how many cans of Coca-Cola were sold by the gas station near your house today? Say they sold 359 cans today. Could they have sold between 350 and 359 cans of cola? Yes. Say 351. Could they have sold between 350 and 351? No. The store cannot sell 350 and a half cans of Coke. Either sells 350 or 351 cans. So the number of cans of cola sold is an example of discrete data. Quantitative data is continuous if measuring how much. How much gasoline did the gas station near your house sell today? Say they sold 5,934 gallons of gasoline today. Could they have sold between 5,930 and 5,934? Yes, they could have sold 3,591. Could they have sold between 5,930 and 5,931? Yes, they could have sold 5,930.5 gallons. Could they have sold between 5,930 gallons and 5,930.5 gallons? Yes, they could have sold 5,930.0001 gallons. Unlike a discrete variable, the unit of measure for a continuous variable can get smaller and smaller and smaller. Quantitative data are always numeric. Because observations within a variable are numeric, arithmetic operations like multiplication, addition, subtraction, etc. are meaningful. Statistical analyses not only include frequency tables, bar charts, and pie charts, but also averages, standard deviations, and correlations. Datasets are cross-sectional, a time series, or a combination of the two, which are called panel datasets. Cross-sectional data are collected at the same time or approximately the same point in time. These data are like a family photo, which shows what you and your brothers, sisters, parents, and grandparents looked like during Christmas in 1996. These data in the photo are frozen in time. Another example involves the number of building permits issued in June 2007 in each of the counties of Ohio. Time series data are collected over several time periods. These data are like a video of you growing up, which shows how you change over time. For example, consider Lucas County in Ohio. Data detailing the number of building permits the county has issued is a time series if it contains the number of permits in each of the last 36 months. Data can be collected from several sources. The company you work for maintains records on workers, customers, and vendors. The government keeps records on its citizens, which includes Social Security pensions, participation welfare, food stamp programs, and unemployment benefits. Statistical studies are used to compile data needed to answer specific questions like, does this pill regrow hair on a bald man's scalp? Have TANF work requirements and allowing mothers to be exempt from these requirements if they are disabled, raise disability rates. Experimental studies first identify a variable to be studied. A good example is golf ball flight after it is struck from a golf tee. However, many variables like golfers' age, heights, weights, health, and years of playing golf, and wind speed, temperature, course conditions, rain, type of golf ball used, and types of shoes worn affect distance. A golf ball manufacturer cannot claim their golf ball flies farther unless they do a statistical analysis, which compare the distances of their golf balls versus other golf balls. Such a study would be flawed if this experiment did not control for the variables listed above. Dumping the manufacturer's golf balls into a bucket with its competitors' golf balls, mixing them up, and then using a robot to hit balls at random means all the aforementioned variables are essentially canceled out. The average lengths of each manufacturer's golf balls can then be used to determine which ball flies further on average. Observational studies make no attempt to control the variables of interest. A survey is a good example. It is one of the more common types of observational studies. Research questions are first identified, which are used to design a questionnaire that is administered to a sample of people. When you book a hotel using www.hotels.com, you may get an email from this website after you stay at one of the hotels you got from their website. They're asking you to participate in a survey. Summing customer ratings and dividing by the number that responded results in an average rating of, say, 3.5 stars out of 5 for XYZ hotel. As I said earlier, statistical analyses of qualitative or quantitative data are more limited than they are for quantitative data. Descriptive statistics summarize data using tables, graphs, or numerical measures such as the average of the proportion. In the Hudson Auto Repair example below, the manager of the garage wants to make the best decision possible. One way to do this is to compile statistical summaries of several variables associated with the operation of the garage. One of the variables of interest is the cost of parts used in tune-ups. She proceeds by randomly selecting 50 tune-up invoices that were stored in a filing cabinet. She enters the cost of parts on each of these invoices into a spreadsheet program like Excel. When she does this, she rounds to the nearest dollar. The data from this sample of 50 invoices is given in this area below. Notice that this data is unsorted and appears to range from about 55 to around 110. We then sort the data from the lowest value of 52 to the highest value of 109. Sorting the data makes summarizing data visually simpler. Since the smallest value is near 50 and the highest value is just under 110, we can generate several convenient intervals having a width of $10. The first interval, 50 to 59, contains 2 invoices. Hence, the frequency of this interval is 2. The second interval, from 60 to 69, contains 13 invoices. Hence, the frequency of this interval is 13. There's 13 in here because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 invoices with parts costing anywhere from $60 to $69. In the next interval, the third one, 70 to 79, this interval contains 16 invoices. Hence, the frequency of this interval is 16. So frequency is just another word for count. The fourth interval, from 80 to 89, it contains 7 invoices. Hence, the frequency of this interval is 7. The fifth interval, 90 to 99, contains 7 invoices. Hence, the frequency of this interval is 7. The sixth and final interval, 100 to 109, contains 5 invoices. Hence, the frequency of this interval is 5. The frequencies in intervals 50 to 59, 60 to 69, 70 to 79, 80 to 89, 90 to 99, and 100 to 109 are 2, 13, 16, 7, 7, and 5. The frequencies sum to 50 because there are 50 invoices in the sample. The percent frequency of interval 50 to 59 is found by dividing the frequency of this interval, 2, by the size of the sample, 50. This ratio is a relative frequency. Multiplying this by 100% gives the percent frequency. The percent frequency of interval 50 to 59 is 4%. The percent frequency of interval 60 to 69 is found by dividing the frequency of this interval, 13, by the sample size of 50. The ratio is the relative frequency, 13 divided by 50. Multiplying this by 100% gives the percent frequency of 26%. The percent frequency of interval 70 to 79 is found by dividing the frequency of this interval, 16, by the size of the sample, 50. The ratio of 16 and 50 is called the relative frequency. Multiplying by 100% gives the percent frequency. The percent frequency of interval 80 to 89 is found by dividing the frequency, 7, by the size of the sample, 50. This ratio, again, is called the relative frequency. 7 divided by 50 is the relative frequency. Multiplying by 100% gives the percent frequency, which is 14%. The percent frequency of interval 90 to 99 is found by dividing the frequency, 7, again by the sample size 50. Their ratio is the relative frequency. Multiplied by 100% gives the percent frequency of 14%. The percent frequency of interval 100 to 109 is found by dividing the frequency of this interval by 50. 50 divided by 50, or 5 divided by 50 times 100% is the percent frequency 10%. The sum of percent frequencies is 100. If these were relative frequencies, the sum would be 1. A histogram is a bar graph, but a bar graph is not necessarily a histogram. The bars of a histogram have no gaps between them, and their widths are equal to the width of the intervals used in the frequency table. If percent frequencies are used, the histogram is a percent frequency histogram. In the above diagram, below the label on the y-axis says frequency. So we're going to construct a frequency histogram. Since the frequency of interval 59 or 50 to 59 is 2, the bar corresponding to this interval stops at 2. Since the frequency of interval 60 to 69 is 13, the bar stops at 13. Since the frequency of interval 70 to 79 is 16, the bar in this interval stops at 16. Since the frequency of interval 80 to 89 is 7, the bar in this interval stops at 7. Since the frequency of 90 to 99 is 7, again the bar in this interval stops at 7. Since the frequency of 100 to 109 is 5, the bar in this interval stops at 5. The total area of the red bars is 50. If I add this area to that area, 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 I'd get 50. If this were a percent frequency histogram, the red bars would have an area equal to 100%. If this were a relative frequency histogram, the red bars would have an area equal to 1. The histogram estimates the true distribution of tune-up parts cost. In most cases, we won't know the true distribution of this variable, or any variable. The area under the true distribution is equal to 1. For the same reason, the bars of a relative frequency histogram have an area equal to 1. The most common numerical descriptive statistic is the average, which we call the sample mean. It is found by summing up all 50 observations of tune-up parts cost. When we add them up, we get $3,949. Dividing this by the sample size of 50 gives an sample mean, or an average, equal to $78.98 per invoice. The sample mean estimates the population, or true mean, which in most cases we won't know. The probability that the sample mean is exactly equal to the population mean is 0, because the population mean is, in most cases, an unknown value. The sample mean, on the other hand, could theoretically be one of infinite many numbers on the number line. Data from the population being studied includes all elements. For example, on election day, the proportion of voters voting for Obama will be known. The names of every voter are the elements. The number that voted for him divided by the number that voted is the population proportion voting for then Senator Obama. A sample is drawn from the population being studied because it is too costly to ask every voter who they are planning to vote for every day leading up to an election. New samples of around 1,000 are selected each day, or every other day. The number that say they are going to vote for then Senator Obama, divided by the number that were in the sample, is the sample proportion voting for then Senator Obama. These polls help candidates decide how to allocate campaign contributions optimally. For example, if polling data tells then Senator Obama that he has no chance of winning Idaho or Wyoming, Obama will spend very little money in these states. This allows them to spend more money in battleground states like Ohio. The sample statistic is used to make an inference about the population parameter it is estimating. This is called statistical inference, which is the process of using data obtained from a sample to make estimates and test hypotheses about the characteristics of the population. If a poll of likely voters is taken, and 53% say they are voting for Obama, then one could infer from this that Obama looks like he may win the upcoming election. Taking a census collects data on all members of a population. Variables included in the U.S. Census are number of children and income. The average of these variables are parameters because there are over 300 million Americans. A sample survey collects data on all members of a population that were selected for the survey. The Current Population Survey, or CPS, gathers information that is similar to what the census collects. However, the CPS is a monthly survey of about 60,000 households. The smaller size is manageable and less costly than a census. Average income computed from the CPS during a census year is a sample statistic, which is probably very, very close to the population mean computed from the actual census. In our Hudson Auto Repair example, the population consists of all tune-ups performed at the shop. From this, we could compute the population mean tune-ups parts cost. Instead of doing this, which is time-consuming and very costly, a sample of 50 invoices were pulled from the filing cabinet containing all tune-ups performed at the shop over its entire history. We took this sample of 50 invoices, added up the cost of the parts on each invoice, divided by 50, and we got a sample average of about $79 per tune-up, or $78.98 per tune-up. The sample average is an estimate of the population mean, which we don't know, and we won't be able to compute in most cases. But if the sample is large enough and representative and random, the sample mean should be pretty close, really, really close to the population mean.